where we kind of left off yesterday. I ran out a little bit of time at the end, so I want to make sure that what we were discussing is kind of made a little bit more concrete for us. We were talking about evaluating functions at different x values, at different input values, and then started the discussion about maybe some procedures that might make that a more efficient process. Okay? So if we look at these two functions here, f of x equals x squared plus 4x, and g of x equals x squared minus 7x, and then the series of evaluations that are being asked here, they're saying f of negative 3 plus g of negative 3, f of negative 1 plus g of negative 1, f of 0 plus g of 0. So they're asking us to continually add f and g together at the same x values, right? Well, we can do that, and we can do that very methodically like we did yesterday, where we take, we'll just do this with the first one, where we take negative 3, and we're going to plug it in here for our f function. I don't know where it went. All right, sorry about that. So we take f of negative 3 and plug it into this function. So remember, and this is going to become very important, especially when there's negative values that are your inputs. And in the upcoming example after this one, the input will actually be another function. So we have to make sure that when we are going to substitute, okay, I'm going to kind of visually, every time I do this, remind myself that I'm substituting the x. So when I do that, I'm going to use parentheses to help with that. If I do that every single time, I will never mess up the order of operations as I start to kind of evaluate that expression. Negative 3 squared is 9 plus negative 12, negative 3. Okay? So we get the ordered pair, essentially f of negative 3. When x value is negative 3, the y value is also negative 3. Okay? We did that yesterday. Now here's the thing. If I don't put parentheses when I make that substitution, I get negative 3 squared with no parentheses, and that's not going to be 9, that's going to be negative 9. Does that make sense, everybody? Sure. All right, so you have to be very, very cautious of that. Now they want g of negative 3. So I'm going to go down to g, and I'm going to substitute negative 3 in. Okay, again, use that idea where it's going to be a negative 3 squared minus then 7 times negative 3. So again, 9, and then plus 21, right? So then that gives us obviously 30. So now we've got the idea that g of negative 3 is equal to 30. They're asking us to take f of negative 3, which was our negative 3, and add to it g of negative 3, which we just said was 30, right? And that turns out to give me 27. So f of negative 3 plus g of negative 3 is 27. Is that okay with everybody? Now, as we did that, it wasn't extremely difficult, I don't think, to substitute that stuff in and to evaluate, but you had to substitute 4 different spots, ultimately evaluate 4 different spots, right? And then one last step of adding like terms in both those. Can we condense that process? And the answer to that is yes, okay? But we can only condense this if we are interested in evaluating at the same x value. So because all those x values of negative 3 are the same, and then negative 1 plus, or f of negative 1 plus g of negative 1, f of 0 plus g of 0, f of 2 plus g of 2, because the evaluation points are the same, we can maybe rewrite this. We can do it a little bit differently, okay? If I have g of x and f of x. And I'm trying to add those together. Let's just kind of do this like this. I should probably have structured the question a little bit differently so I don't have all this. So I give myself a little bit more room, but it shouldn't matter. G of x plus f of x. I'm going to take f of x as x squared plus 4x. Okay? And then I'm going to add to that. So that addition right there is that addition. Is everybody okay with that? Okay? Then I'll put g of x in. X squared minus 7x. And now I'm going to condense and do the algebra. So the algebra that I'm about to do here, guys, is the algebra essentially that was getting taken place right there in both those. Okay? So then we'll get 2x squared minus 3x. So f of x plus g of x can actually be rewritten in algebraic terms as 2x squared minus 3x. Is that okay? Okay, now here's the reason I want to do this. If this is going to be f of negative 3 plus g of negative 3, well, doesn't it make sense to come down here and say, okay, 2 times negative 3 squared minus 3 times negative 3? And there you substitute how many times? Just twice, right? Okay. Negative 3 squared. 9 times 2, 18, right? Negative 3 times negative 3. Positive 9, what's that give me? The same 27 that we got that way, right? Okay. Now, if I was only going to do f of negative 3 plus g of negative 3, that stuff that we did in black there is probably more work than what's necessary. You're probably just going to evaluate an f and evaluate a g and then add them together, right? But because they're asking me to do this over and over and over again with 4 or 5 or 6 different input values, I think, in my opinion, that this is going to be much more efficient. Okay? So what we like to do, just a notation thing here. Let me get this out of the way. Is that we like to take that f of x plus g of x that we just came up with, and we called that, it ended up being 2x squared minus 3x, right? We like to eventually, instead of referring to it as f of x plus g of x all the time, this is actually a new function. So let's call it a new name. Let's call it h of x. You call it whatever you want to, but usually h is the next one that they use. And now when they say find f of negative 1 plus g of negative 1, well, that's asking the same question as find h of negative 1. And now, in my opinion, it becomes a much easier procedure, right? Negative 1 squared is 1 times 2 is 2, plus 3 is 5, right? So remember what that gives me, negative 1, comma 5. Previously, when we had this one, we had negative 3, comma 27. Okay, now we do f of 0 plus g of 0. Well, that's the same thing as asking what is h of 0. Hopefully, you don't even have to write this one down. Plug in 0, but that's going to vanish, right? That's going to go away, and you're going to get just 0, correct? So 0, 0. We do g of 2 plus f of 2. Same thing as asking h of 2. Okay, so we get 8 minus 6. 2 comma 2. We'll do one more. H of 3. So 18 minus 9, which gives me 9, right? So here's the idea. And we did, 5 of those? If you were evaluating like we did in red, where you took 0 and plugged it into G, and then took 0 and plugged it into F, and then added those together, and then did 2. plugged into G, and then plug 2 into F, and then you add those together. You would still be doing the work, while somebody that did the stuff in black, where we renamed everything, they'd be done and on to the next problem. Maybe the next problem after that. Does that make sense? So it's an efficiency thing. But I want to talk about what this means graphically as well to us. Okay? So if I take f of x, which we said was x squared plus 4x, and we go g of x, which was x squared minus 7x, okay? Those are the two graphs we're talking about, right? Okay? Well, when I ask you to evaluate at x equals -3, when we ask to evaluate at x equals -3, what we're essentially doing is taking this x equals -3 line and seeing what is then the y value of where that vertical line intersects your two curves. So that vertical line and the red curve are going to intersect right there, right? Now we know that the x value is -3. We know that. We chose that. We chose that line of -3. And then you see the output that goes with that is also -3, right? Isn't that what we found for f of -3?
Yeah.
We found the y value of the f of -3 to be -3. I want to do the same thing then for this equation in the purple graph. And when we plugged in -3 to g, we got 30 back. And just kind of remembering that, got that 30 right there, right? Graphically speaking, you can see then that we're intersecting that purple graph up here at 30. Okay? If I were to add those two numbers together, 30 and -3, we get our -27, right? So what I'm going to do is I'm going to write -3, comma, 27. Now that point, zoom in, that point is not on either of those curves, right? But we're going to talk about what curve that does show up on here in a moment. If we said x equals, what was the other one? We did -1. Okay, so now we're getting the -3 and the 8 that we're adding together, and we get what when we add those together? 5, right? So -1 comma 5 was an ordered pair that we came up with, but that point is not on either of those curves. We had 0, 0. Okay, so I'm just talking now about these results that we got. Okay, 2, 2, and 3, 9, right? Now, none of those points, I guess E is just because of the nature of the next thing that we're going to do. But these points are not on those curves, right? D's not on it, F's not on it, G's not on it. Okay? So if I hide this information, okay, those pieces of information right there are part of a third graph. That third graph that they're part of, if I take f of x plus g of x, which gives me x squared plus 4x, is what we did algebraically, right? Yeah. You see how those points then show up on that curve? Okay. So when you guys, when we say that we can either evaluate individually, okay, and then do the algebra between those evaluation points, or we can take the algebra, we can take the algebraic expression and add it together, and then evaluate in that, you're getting the same results. Okay, but that's the logic behind it when we look at the graph. Now, here's the thing. That only works if this input here is the same as that one. It will not work if one of those is -3 and the other one's 7. Okay? You would have to evaluate them separately then. Does that make sense, everyone? Okay. All right, so yesterday we were working on these, and we got down to, I don't think we do C. I don't think we did C, but I want to work on part D here. So let me take that. All right, so part D says you take these two functions, f of x and g of x, and instead of inserting specific values, you're going to insert variables. But those variables represent values, right? They represent numbers. So it's the same procedure. It's the exact same process. Okay? So the first thing I'm going to do is I'm going to take f, and wherever I see the input value, I'm going to replace it with b. Okay, so previously this was x, now it's going to be b. This was x, now it's going to be b. So it's going to look as radical b plus 1. Is that okay? I'm then going to do the same thing for g. Okay, but everywhere I see the input of x, I'm going to replace it with a plus 1. So it's going to look. Now, understand this is where it becomes very crucial to make sure that when you're inserting this, especially when it's a quantity, that you put parentheses around the thing that you're inserting. So the negative stays, and now my x is an a plus 1. We'll square that, and we'll add 2. Okay? Now, you see it on the whiteboard up here, this here would be the sum of f of b and g of a plus 1. Does that make sense? It's just taking those two things we have in red over there, slapping a plus sign between them right there, and we've got their sum, right? But is there some terms there that could be added together? Yes. Yes, okay? And there's actually some hidden terms in there that can be added together, because we got that binomial squared, right? So when you do this, you need to continue evaluating these things that can be maybe simplified, okay? Or we want to expand it and then condense like terms. So here I've got a negative, but a plus 1 squared, that turns into a squared plus 2a plus 1, right? Plus then 2. Then I'm going to distribute that negative through. And now I've got these like terms of negative 1 and 2. So we get negative a squared minus 2a plus 1. Now sometimes that thing itself might be able to be maybe factored down to like a binomial square or something. I'm not going to worry about that or try that here. But sometimes maybe that'll turn into like x squared minus 5, or sorry, minus 25. So it might be beneficial to maybe rewrite that in a different way. Okay, so now I've got f of b and g of a plus 1. And now I'm going to merge those together. So f of b plus g of a sub, or a plus 1 is going to look like radical b plus 1 minus a squared minus 2a plus 1. And that blue statement then is what we're interested in on a test, on a quiz, homework. Web Assignment is going to ask for that simplified version. Is that all right?
That's final answer.
Final answer. A lot of times, depending on what they choose, so sometimes what they'll do is when they create problems, they reverse engineer them, so they kind of start with what they want the answer to look like, and then they work backwards to see what do we need to present you with as the original problem so we can get to that answer. So a lot of times they'll want that, they'll start with a very concise looking f of b plus g of a plus 1 kind of answer, and then work their way backwards. So sometimes that I think looks kind of messy, right? Maybe in your homework they're not that messy. Okay. Questions on that?
Yes, sir.
That procedure is going to be very critical for us in the next couple sections. We start talking about composite functions. Okay. Here is so the remaining portion of what we talk about today is just additional ways of interpreting functions, gaining information from functions, whether we gain that information from the graph or from the equation. But we have to understand the notation. Okay. So here's the thing. They're asking us, says use the graph to find f of 0, f of negative 2, f of 3, and the values of x such that f of x equals negative 3. So we got 4 things here we're trying to find. It would be so much easier. It would be so much easier if they said, if the x value is 0, what is the y value that goes with that? If the x value is 0, what's the y value that goes with that? It's 1, right? Okay. So when they say f of 0, we get 1 back. Okay. And like I said, that would be such a simpler thing to do if they said, if x equals 0, what is the y value? Okay? And I think mathematics in general would be so much more simple for everybody if directions were more explicit. Okay? But hopefully you can realize why mathematicians would not want to write that statement. If x equals 0, what is the y value? So they create their own notation that says f of 0 says that same phrase. Does that make sense? And we have to be able to understand that. We have to be able to read that. Okay? I think one of the most important, I wish we had a class that just taught you how to read math. Okay? Not necessarily do the math, just read it. Understand what the notation is, that type of thing. It would make things so much easier for you. If you remember, that's the x value. That then is my f of x value. So as an ordered pair, x comma f of x, this ordered pair would be 0 comma 1. Okay. If we do f of negative 2, okay, we're now asking if the x value is negative 2, what's the y value that goes with that? Negative 3. Okay? So negative 2 comma negative 3 would be the ordered pair that statement is referring to. F of 3. I think it's talking about 3 here. It's kind of hard to see, maybe a 3 or 4. I think it's saying 3. Okay? Now, the next part of this question, a little bit different. The next part of this question says, what? Okay, so when I write f of x equals negative 3, it is saying, what or plural are paired with a y value of negative 3. It would be so much simpler if that was the phrase they gave us. They, as mathematicians, say f of x equals negative 3 says that statement. It implies that statement. Okay? So when I look at that, f of x equals negative 3, what are these input values of x that would produce an output value of negative 3? Good. I heard negative 2 and positive 2, right? So negative 3 would be that line right there. That line is what we're talking about right there with that negative 3. What are the x values then for the points that show up there and there? Those x values are negative 2 and 2. Now that's not an ordered pair. Okay? So put those in braces. If I want to write it as ordered pairs, it would be -2, -3, and +2, -3. Those would be the ordered pairs of those two positions. So I've been teaching this course for, it's been like 12 years, but under Rhodes's kind of governance, it's been about 5 years. And they write the final. This question, or a version of this question, has been on each one of those finals. Okay? So this is a very important thing for us to understand. Okay? And to be honest with you, in those 5 years, a good amount of people answer f of 0, f of -2, f of 3 correctly, but then they get to f of x equals -3, they just kind of fall off the deep end. They have no idea what's going on there. Okay? It's just now asking what is the x value that goes with this particular y value. Okay? And obviously these, because of the definition of a function, those are only going to have one answer, right? Okay? Because every x value is paired with only one y value. But the definition of a function does not say that every y value is paired with only one x. Some functions have that added feature, but a lot of them don't. Okay? So because we have f of x equals -3 there, that is saying that it is okay, because of the definition of function, it is okay to have multiple answers for that. Okay? Does that make sense? Because when I'm done, I get the point -2, -3. Well, -2 only ever gets paired with -3. +2 only ever gets paired with -3. So there, we do not violate the definition. Okay? Is that all right? These we've already done. Okay? We did them yesterday in a ordered paired kind of format. So when they say input, output, remember your input is your independent variable, or x. Your output is your dependent variable, f of x. So if I write these as ordered pairs, we have 2, 1, 5, 3, 8, 6. Remember, the first thing we were going to do is see if 2 ever repeats as an x value. It doesn't, so I go to the next one. Does 5 repeat as an x value? Nope. Does 8? Nope. So if they don't repeat x values in my ordered pairs, it's automatically going to be a function, because it's going to satisfy the definition. Okay? If I look at the next, so that one is a function. If I look at the next one, we've got 1, 0, 5, 2, 5, 4. Okay? 1 doesn't repeat. Does 5 repeat? Yes, it does. So now, just because it repeats does not automatically give you your answer. You now have to see what is it paired with. In this case, it's paired with 2, and then it's paired with a different value, 4, right? So if you were to graph those, they would be stacked on top of each other, right? Be 2 different points stacked on top of each other, 5, 2, and 5, 4, which would make it fail the vertical line test. So this is not a function, okay? Because we violate the definition that says every x value is paired with only one y value. Do not make me kick you out of this class. The next thing we want to look at is the idea that if I've got 5, 2, 5, 4, let's do this. Let's go 7, 6, and replace this one here with a 2. So I've got 1, 0, 5, 2, 5, 2, 7, 6. And showing this example, I just want to make sure that we understand, just because the 5 repeats as an x, that is not the process to determine whether this thing is a function or not, right? The process is, does the x repeat with a different y value? And in this case, no, it doesn't, right? So that would represent a function. That would pass the vertical line test. All right, I want to write something. Well, let's do this. So we've been talking about this vertical line test. Okay, does that thing pass the vertical line test? Yes, it does. Okay. Does that pass the vertical line test? No, it doesn't. Okay. So every time that we do these guys, okay, every time that we deal with determine whether something's a function, there's a set of kind of concepts that we want to think about. We want to think about the ordered pairs. We want to think about the algebraic expression. We want to think about the graph. We want to kind of think about these things at all the same time, okay? because different aspects of them are going to help you determine function or no function, and then if it is a function, maybe some critical things about it. Okay? So this, I think, is the hardest thing. Okay? Graphically, it's very easy to see the vertical line test passes, right? I think ordered pair process with a tabular form, I think that's pretty easy as well. I hope it is. If you struggle with that, graph them, and then you revert to the vertical line test approach, which we should all understand. But this is a little bit more difficult. Okay? Now, you can answer a lot of these by knowing what these graphs look like. Okay? And that's kind of the structure of this course, is to be able to look at each one of these and know what the graph looks like. Anybody know what that first one looks like? Parabola, right? Okay? That is we call it the parent function for our parabolas. Okay? It's the most simplistic, basic, quadratic that we get. So is that going to pass the vertical line test? Yes. Okay? Now, that's basically, taking an equation and converting it to its ordered pairs, which, if we come up with the infinite ordered pairs, we get the graph, and then applying the vertical line test. We should be able to kind of understand this algebraically as well. Okay? What that rule says is that you put in an x value, right? Put in any x value you want. Okay? So if this is a function, then I should be able to replace that x with anything and get a y value and only one y value, right? Give me an x value to plug in.
700.
Okay, if I plug in 700, what am I going to get back? Well, what's 7 squared? 49, right? What's 100 squared? 4 zeros, right? So I get that back. Okay? Will I ever plug 700 in and not get the same thing back? No. Okay? No matter what number you choose, when you plug it in, you're going to get that value back and only ever that value back. Okay? Where if we go to example 2, okay, anybody know what example 2 looks like from conic sections? Because it's a parabola that opens this way. If we understand that graphic, then it's easy to say that fails the vertical line test, right? So let's look at the algebra. Okay? Choose an x value. Choose an x value. What do you want your x value to be? Give me a number. In fact, I can't use 20. Okay. So if I put 20 in here, okay, my x would be 20. The y value then would be what? If I've got y squared is equal to 20, what's the y value going to be? No.
I don't know what 20 squared is.
It'd be the square root of 20, right?
Oh.
But it's going to be plus or minus. So now, for the x value of 20, I get positive radical 20, and I get negative radical 20. Is that a violation of the definition of a function?
Yes.
Yes, it is. Okay? Does anybody know what the next one looks like? What? A swoopy? If we graph it, so we'll do this in a moment. It looks like that. Okay? Y equals the absolute value of x would be the v that we're familiar with, or comfortable with. Okay? If I go y, the absolute value of y equals x, it actually kind of, I don't want to say inverts it, but it's now open to the right. So here's the idea. Give me an x value. Give me a positive. Again, it doesn't matter. Again,
69.
You hurt my head. All right, 12. So absolute value of y is equal to 12. Okay, you choose the input, right? So now here's my question. What values can you put in for y so that you get 12 back? Yeah, you could put positive 12 here, and that's going to give you 12. So that would be the ordered pair 12, comma 12. Okay? So this would, remember, that's the x. That one's going there. This is your y. So that one's going there. I could have also put negative 12 in and still got 12 back, right? So now that means that I had the order pair x being 12, but y was negative 12. Does that violate the definition? Yes, it does. Okay. When I look at that example 4, what's example 4 going to be? What's the graph of 3x plus 1? Just a line, right? Any line, unless it's vertical, any line is a function, right? It's going to pass the vertical line test. Okay. I'm going to show you something here, which hopefully you've seen before. Let's just write all polynomials let's write it this way. All polynomial functions.
Pardon interruption. Mrs. Beckman's Wildcat Time. Those students in Mrs. Beckman's Wildcat Time should report to Mr. Gomez's room, room 217. Again, those students who are in Mrs. Beckman's Wildcat Time should report to Mr. Gomez's room, room 217 today. Thank you.
Okay, so as I write this, we've got the n. We'll talk about what these terms mean here in a moment. But you can see it a sub n, x to n. A sub n minus 1, x to n minus 1, right? That subscript and this exponent are the same, right? In each one of these?
Yeah.
And it's decreasing by 1. It's n minus 1. And this would be n minus 1 minus 1, which is n minus 2. The next one would be n minus 1 minus 1 minus 1, would be n minus 3. Okay? These ellipses tell me that that pattern is going to continue, right? We eventually, let's say this n was like 5. This would be 4. This would be 3. Eventually, it keeps subtracting values of 1. I would get down to an exponent of 1 eventually, right? Well, if I subtract an exponent of 1 from that, I would get to 0 eventually, right? Okay? So I'm going to write this as x to the 0. But what is x to the 0 the same as? Not 0. 1. So a lot of times we don't write it. We just write a sub 0. Okay? That ends up actually being a constant. That ends up being just a quantity that has no variable component to it. Every single polynomial is of that form. Okay? So if I look at 3x plus 1, 3x plus 1 is of that form. Because I've got a coefficient of 3, x to the first, plus then some constant. Does that make sense? So that portion right there is a linear polynomial. Okay? If I go like 6x squared plus 4x plus 1. Okay? So you see here, if in this case my n value would be 2. Does that make sense? For my exponents. So we're starting at 2 here. This would be 2 minus 1, wouldn't it? So that's my n minus 1. And this would be 2 minus 2, which would be x to the 0. So there's my constant. We could have, so that's a polynomial, okay? We could have something like 5x to the 8 plus 3x to the 7th plus. And now I'm going to come down here and go 5x squared plus, and then just say 4. And I'm putting a lot of plus signs, but they could be minus signs as well. If I had 5x to the 8th plus 3x to the 7th plus 5x squared plus 4, that's a polynomial. Okay? Now you might say, well, no, it's not, because it's not following this structure. You started with 8 right here, so this one here should be 7, so the next one should be 6, right? And it is. There's an x to the 6th here, but what's my coefficient out in front? And 0, right? Does that make sense? And then I've also got 0x to the 5th, I've got 0x to the 4th, and I've got 0x to the 3rd. And then over here, we've got 0x to the 1st. If I write it that way, you see now that the exponents are going from 8 to 7 to 6 to 5 to 4 to 3 to 2 to 1 to 0, right? Now my coefficients out front in the description, we say they're a sub n minus 1, a sub n minus 2. That notation is just to allow us to know that a sub n goes with this variable term x to the n. This coefficient of a sub n minus 1 just pairs up with the x to the n minus 1, right? So the a sub n minus 1, we're really not doing anything with that. It's just telling us that that's ultimately our second coefficient in the list. A sub n minus 2 is our third coefficient in the list. A sub n minus 3 would be the fourth coefficient in the list. Does that make sense to everybody? Okay. The reason I'm saying that is when we are looking at an equation and asked to determine if it's a function, if it is of that form, if your equation is of that form, the answer is 100% of the time yes. Okay? Every single polynomial is a function. Every single polynomial is going to pass the vertical line test. Okay? Does that make sense? Okay? Now we still got 5 minutes, guys, so don't pack up. We still got some stuff to do here. Finding the domain and range of a graph. Okay? Finding the domain and the range of the graph. Hopefully you've already had some exposure to this, but this is probably one of the most important things that we're going to talk about all year. Okay? And if it's not until, mid-November that you really pick up on what domain and range is, you're going to miss out on a lot. Okay? Domain. Anybody remember what the domain is? The domain is all x values that a function is defined for. The domain is all the x values that a function is defined for. Ultimately, it's the collection or the infinite list of all the x ordered or x coordinates of all your ordered pairs. Okay, of a graph or a function. A range then is the what? Yes, all y values that a function is defined for. Okay. Doing this first one, this is the way we're going to structure this. We're going to say capital D and a semicolon. So we're talking about a set here, capital D. It's going to be a set of solutions. And the way that you do this with domains is that you're going to draw a vertical line, whether you physically draw it or mentally superimpose it. You are going to do this. You're going to move that vertical line from left, furthest part of your graph on the left, and move it to the right. And you're going to keep track of the first values that we interact with. What will be the first value the first x value that my graph starts to interact with? 2, right? Does that make sense? Okay. That would be if I were to list all the ordered pairs in order for this graph. 2.0, an infinite number of times, comma 1 would be that first point, right? Does that make sense? So 2 is the first domain value that we're interested in. And I'm just going to keep track of all the domain values, all the x values that I'm using. What's the last x value I would use? I would use 8, right? So the domain, do you guys agree, would be all the x values that fall in the interval 2 to 8. Yeah. Okay. Now, if there were any domain values in between there that were open dots or breaks in my graph, we would have to make note of that. Okay? But that's how we do the domain. Now, usually people, after a little bit of work with this, get the domain 100% of the time. The range is the one that, in the past, that I've seen a lot of struggles with. And it's because of the structure that you want, how to come across this, okay? We're going to use a horizontal line, but we're going to read from bottom up. I think people want to read graphs left to right, top to bottom, because that's how we read prose writing, right? Left to right, top to bottom. But with a graph, you want to go bottom up, okay? Because it's then going to put my range in chronological order. If I go bottom up, what is the first y value that this is going to intersect with? 6, right? Now I include 6 because it's a closed dot. And now what's the last y value that I want to interact with? 8, closed or open? Open, so parenthesis, right? Okay? If I went top to bottom, I would have had 8, 6. And remember, our intervals need to mimic a number line, right? 8 does not come before 6. So we need to go bottom up, and that will always put our number line in order. What that is, guys, if I were to ask you to list all the ordered pairs in that segment, would you be able to do that? No, there's an infinite number of them, right? Okay. But writing the domain and range that way, you now have provided me that infinite list of ordered pairs. Quiz tomorrow over functions. Functions, that's it.
That's like what we just wanted, right? Was it like this,
Just functions tomorrow.